All right, so basically this chapter is about how phases are, different phases of a compound or different phases of a substance can be manipulated. That's probably the best way of putting it. This is kind of a big engineering thing. So we're going to get into solids here, something called elasticity, or what we, the section called elastic moduli, ways of measuring stretchiness. So elastic means expanding material without breaking or snapping, whatever we want to call it. The stress point is another term that we're going to use here, where it's the limit at which the material breaks or snaps. So if you get to a point, like a rubber band, you get to a point where you stretch, but if you put too much force on it, it just snaps up. So mathematically speaking, that stress is defined as the force over area. It's a pressure. So the label for that is newtons per meter squared. Strain is a comparison of the change of the length with the original length. So you're putting a strain onto a material as you stretch it. And that is defined as the absolute value of the change of the length with the original length L sub O. The comparison then between the stress and the strain then becomes an important factor that we can measure for each material, whatever that is. And that's called the Young's modulus. And Young's modulus, the letter Y, is stress divided by strain, where you take your stress, which is force over area, and your strain, which is your change of length with the original length. So the label for that, when you measure this, the stress is newtons per meter squared, as we had just seen. And both of these are measured in meters, being SI units. They cancel out, so this gives you newtons per meter squared as the label for Young's modulus. There is a list of Young modulus numbers on page 314 of your textbook, so any problems from that can be obtained from there. The example here. Let's suppose you have a nylon string that has a diameter of 1.20 millimeters, and it's exposed to a 15 Newton pressure or tension force, not a pressure, but a force that can stretch out how far. So we want to calculate how far we can stretch it before it starts to snap, or just be unusable at that point. So we use the formula, y equals that nonsense there, and we know the value of y is 5.0 times 10 to the 9th Newton per meter squared. We got that from the book on page 314. The force in this problem is 15.0 newtons. The area, when you take the cross section of the piece of nylon, we're assuming it's going to be a perfect circle, so that's pi r squared. So we have to change that radius, which is given to us as 1.20 millimeters. The diameter is 1.20 millimeters. We change that to the radius of 0.600 millimeters. And then because we want everything in SI units, we're going to change that to meters, and that's going to be 6.00 times 10 to the negative 4 meters, giving us an area of pi times that value squared of 1.13 times 10 to the negative 6 square meters. The original length was 50 centimeters. We changed that to meters, 0.500. And then the example I gave you on the script shows one way in which you can apply the mathematics. Another way that I wanted to show you is how you can actually rewrite the equation to get your unknown variable by itself. Our unknown variable in this case is going to be the change in length, the delta L. So I multiply both sides by the denominator here, which is a times the absolute value of, well, I'm sorry, let me back up here. I took this and I changed this into a fraction without a fraction within it. So this is f over a divided by this. Change that multiplication, switch those around. You get f times LO over a times the absolute value of the change of L. Now I multiply both sides by a times the change, absolute value of the change of L. And that gives me YA times the change of L equals f times LO. And you get this by itself, we divide both sides by y times a, Young's modulus times the area. And that gives me F times LO over y times A. Plug in the numbers. I get 1.33 times 10 to the negative third meters, which is 1.33 millimeters. So we could stretch at 1.33 millimeters, and at that point it's going to stretch. Right? So use that formula, use either process, it doesn't really make any difference for the 5 practice problems that you're given. Okay? Have fun.